So we have two talks today, one from, I guess, the US Atlas R&D program, and then one that's an IRIS-HEP fellow. So we'll go ahead and get started. Kyungeon is going to talk about real-world applications of ServiceX and an analysis data transformation system.
Okay, thank you. Hello, I am Kyungeon from UT Austin. Today, I'm going to talk about one of the IRIS-HEP project, ServiceX, and specifically focusing on its real-world application. And just want to remind you that ServiceX is one of IRIS-HEP project on the area of data orientation, management, and access, primarily for the challenges at the high-limit LHC area. Although I'm not going to discuss the architecture of ServiceX itself today, let me briefly introduce what is ServiceX. Like other IRIS-HEP projects, ServiceX utilizes non-traditional HEP tools. It's built on an extensive ecosystem of open source technologies, mostly driven by industry. For example, each microservice of ServiceX backend is built as a Docker container, and ServiceX is deployed to Kubernetes cluster, which orchestrates containers. And it also employs somewhat familiar tools like Lucio to access data on the grid, and Pythonic HEP tools like Umroot and Auto-differentiation. So what is ServiceX? ServiceX is a scalable HEP event data extraction, transformation, and delivery system. Let me start with HEP event data. ServiceX is experiment agnostic as it supports various data formats as input. At the moment, Atlas XAUD or DAUD, CMS Nano AUD, and Root flat antables are supported, but other data formats or future data formats can be added in the future. And extraction is the core of ServiceX. It selects only necessary columns from the input and also rows of the selected columns via filtering, and then transform those selected columns in a data format such as array, a batch parquet, or root antable. Finally, selected and transformed data can be delivered to user, or it also can be streamed into an analysis system. And as mentioned earlier, ServiceX runs on Kubernetes cluster, so it can automatically scale the workers when needed. So as a user, let me show you how to get data via ServiceX. ServiceX provides a nice front-end library written in Python to interact with the backend of ServiceX. You first need to import relevant packages. Those are available in PyPy. And first one is the main front-end library. And the second one is a helper package to translate root TCA syntax into the language that ServiceX understands. And then define the grid data set in Lucio dataset ID and write your query. The query includes the name of input T3 and the list of columns or branches you want to deliver and the selection you want to apply. And then define ServiceX dataset with the dataset you want to read and the backend type for that dataset. Here I use the backend type of Umroot, assuming the input data is root flat antable. And finally, ask for a data delivery in the format of array. Now, ServiceX deployed at Kubernetes cluster starts to read files in the Lucio dataset from the data center and extract, transform, and deliver to you. Here I put data center and Kubernetes cluster inside the same box to emphasize they are co-located, because the performance is really limited by the network speed between data center and Kubernetes cluster. In principle, I can deploy ServiceX into my laptop, which is something I often do, but just for testing purpose. But in that case, fairly large amount of data need to be transferred over the network and slow down the whole process. Let me show you a recorded demo that uses ServiceX deployed at University of Chicago River Cluster and reads 76 gigabyte of data set stored at Midwest Tier 2 and deliver a column after pre-selection to my laptop in South Korea. So it's basically the same Jupyter notebook that I showed, but with real values. And like it also imports packages and define visual data set and construct query. And here I want a column Lepton PT1, and the selection of Lepton PT1 is larger than 110 GB and is less than 2.4, and from the nominal tree. And then I define ServiceX dataset and delivery request. So now it submit request, and now it shows two progress bars, one for transformation and the other for download. And you can see there are 6 files in this data set. And if I wait a bit and it's transferred, and now it starts to download from the Kubernetes cluster. And yeah, now I have the data in the format of a array. And I hope you are convinced that it's pretty easy to use. Let me talk about what ServiceX can provide to the analysis workflow. This diagram shows the simplified Atlas run-to analysis workflow in black lines, and also alternative workflow using ServiceX in red and orange lines. Once we have full information in the format of AOD after reconstruction, and then we produce various derivations from the AOD, depending on the interest of fixed analysis groups. And then each analysis group usually further reduce the data by producing final identitals. And this workflow has been very successful, but it requires sizable computing resources and dedicated software for each step and time. On the other hand, ServiceX can access directly to the upstream of the pipeline and deliver early information that user needs. And in principle, it can save lots of disk space and possibly CPU and time. So now we have an interesting building block, I would say, ServiceX, to construct a new analysis workflow. And I will discuss the integration of ServiceX into an existing analysis workflow, and especially with a minimal change from a user perspective. So let me introduce the software framework that I integrate ServiceX into. The TREX-Peter is a statistical analysis framework used by many Atlas analysis for statistical inference via profile likelihood fits. A user need to provide inputs in the format of root antipole or histogram and a single configuration file to steer the framework. And TREX-Peter basically does the rest for you. It produces root-fit workspaces, perform fits, and extract limits, and produce pre-fit post-fit plots. And it also generates paper quality plots and tables, and also provides many diagnostic tools. In the current workflow, you need a direct access to the input root files where TREX-Peter runs. On the other hand, ServiceX can provide an alternative workflow by delivering minimal information directly from the grid. So we wrote a Python package that delivers minimal information for TREX-Peter using ServiceX. The package employs under ServiceX to read flat root antiples from the grid, and ServiceX front-end library to interact with the ServiceX backend, and take a library to translate the Rutica syntax used in TrueXPeer configuration into the language ServiceX understands. And finally, Parquet to root converter to convert outputs from ServiceX in the format of Apache Parquet into root entiples. You would say usage of the package is fairly simple. You need to import the package and define the instance using the same TrueXPeer configuration file you use for other TrueXPeer steps, and then ask to deliver root entiples. And the package then analyzes the configuration file and make ServiceX requests for data delivery with proper selections and prepare deliver data in the structure that TrueXPeer understands. One nice thing is whenever you make a change to the configuration file, all the necessary ServiceX requests are made due to the caching feature of ServiceX frontend library. This is a side-by-side comparison of TrueXPeer configuration files. Left is the default configuration when reading input root entipole from local paths, and the right is the same configuration, but for the workflow using ServiceX for TrueXPeer. I'm not gonna touch the details of configuration, but highlighted the required changes for ServiceX TrueXPeer. The top one is a flag, use ServiceX that need to be set as true in the job log. And since ServiceX read data directly from the grid, each sample needed grid dataset ID. So user doesn't need to write a separate file to use the package, just use the same configuration file for the rest of TrueXPeer steps. Let me compare current workflow with the one with ServiceX. Let's say we have a final root entiples produced on the grid. And current workflow is we need to download all entiples from the grid to a local cluster or some US area or your laptop, as shown in the diagram, and then run TrueXPeer to generate histograms from the downloaded root entiples. In the ServiceX workflow, instead of downloading all files, run ServiceX for TrueXPeer to deliver all the information needed to generate histograms, and then run TrueXPeer on the delivered data by ServiceX to generate histograms. From a user perspective, downloading data from grid using Ruscio is comparable to downloading data using ServiceX for TrueXPeer, or maybe easier since you can use the same configuration file to do that. Finally, let me show how the performance is with ServiceX. I used a realistic configuration file that is currently being used by an analysis, and it uses 17 samples and considers 34 systematics. And total size of root entipole is about 650 gigabyte. And I use ServiceX backend deployed as University of Chicago River cluster. And from the current workflow, first thing is to download 650 gigabyte to UT machine, and it takes at least a few hours. If network is not fast, and if you can download like something like 50 megabyte per second, and it still takes about 4 hours. Then you need to run TrueXPeer to generate histograms out of 650 gigabyte root files, and it takes slightly more than 2 hours if I use single core. If you do ServiceX workflow using ServiceX for TrueXPeer, it makes 115 ServiceX requests, and it takes 7 minutes to deliver root entiples from the grid. And since the delivered data is much smaller, it takes only 2.5 minutes to run TrueXPeer to generate basically the same histogram as the current workflow. If you compare work time of both workflows, ServiceX provides at least a factor of 10 faster than current workflow, even ignoring the time for download. And more importantly, you can save something like 649.6 gigabyte of disk space. And recently we published an instruction of ServiceX for TRXsphere package at the TRXsphere reader page. So it's now open to public. So let me summarize. So ServiceX provides novel data delivery methods to the existing workflow by using the state-of-the-art technologies. And as shown in the previous slide, integration into the popular statistical analysis framework shows really remarkable performance improvements. And I want to emphasize that a low barrier would attract more people to try ServiceX, and now it's available to public. And this work also will be presented at IRIS-HEP next week. And there are also other ongoing fascinating applications like the integration into Kafka, and still many potential applications using ServiceX at various stages of workflow. That's all. Thank you for your attention.
Great, very interesting. Thank you. Who has questions? Just get everyone into being silent. I guess I had one, maybe slide 12 is as good a spot as any. I wanted to understand. So if I'm instead of wanting to use ServiceX for TRXfitter, I want to use it for FooFitter. How complicated is that, or what do I have to do to write the ServiceX for FooFitter function?
So ServiceX, provides, basic building block in your analysis workflow. So yeah, depending on your software or latest tab.
So I guess if I'm doing something somebody's already implemented, then I don't have to do anything. But if I'm doing something, I have a new, I don't know, I'm using an object-oriented T-tree or something. I guess that then I have to potentially have a customized layer for my own
right. Yeah.
thing. Okay.
Would it be fair to say, that the hardest part was the integration with TRXfitter, not the integration with ServiceX?
In which sense? In the sense that the resulting T-tree was just in a different format and had to be the TRXfitter had to be adopted. Is that what you mean?
I would say, ServiceX is, very powerful in a way that it can deliver the data in easy to integrate with Python ecosystem. But TRXfeeder is like a traditional workflow, so everything is in root and it has its own configuration structure, not JSON. So those things takes bit amount of work, but still we thought it's worth to integrate that because that is more familiar to the many users.
Okay, good. That makes sense to me. Thank you. Anyone else with questions or comments? Looks like Ben posted a link to some more examples in the
I'm about to post a link to. I'm going to post a link to Kyungeon's source code that shows you all that was really required to implement what you've seen. So, like when you were saying, if you wanted to write a wrapper for another fitter, how much code is there? And you can see there's not a lot of code here in the actual adapter between TRXfitter and ServiceX.
Oh, perfect. That'll help me answer my own question. Thank you. Any other questions? Otherwise, we'll move on to the next talk. Great, thanks again. I think that was really interesting. Just to give you a 2-second introduction. So Anish is finishing up an IRIS-HEP fellow working with, I think, Jim and Lucas on differentiating awkward arrays using JAX. So go ahead and give a presentation and we'll ask questions at the end, I think.
Sure. Thanks, David. Hi, I'm Anish Biswas. I'm a junior at Manipal Institute of Technology, India. I was an IRIS-HEP fellow for the past 4 months under the mentorship of Jim and Lucas, and I was working on enabling differentiation on functions containing awkward arrays using JAX. This talk would be an overview about how far differentiation has come along for awkward arrays, and as well as the steps we took to get there. So this project is one of the smaller pieces that might be able to solve the grand analysis challenge of IRIS-HEP. So what is this grand analysis challenge? Well, this grand analysis challenge involves the development of tools that will lead to end-to-end differentiable physics analysis. So NEOS is currently working on figuring out how one can make the non-differentiable parts of the pipeline differentiable, for example, histograms, so that the gradients flow throughout the entire pipeline. My work, however, was more focused on the initial side of things, where the data comes in the form of awkward arrays, and how we differentiate functions that make up an observation in the immediate next step. Okay, so what were the goals of this project? So before defining the goals, our choice of the auto-differentiation tool was JAX, just because many people in the grad group were using it. So JAX is just NumPy on CPU and accelerators that had a very good auto-differentiation support. So one of the goals of this project was to figure out whether or not we could use JAX to enable differentiation of functions involving awkward arrays. And since JAX can only differentiate data buffers which are rectilinear or linear, and awkward array is not a rectilinear data structure, it's a ragged data structure. So it becomes a very good problem to explore. Second, whether this resulting architecture could handle the most commonly used differentiation use cases. And finally, we'd really like to do better than write another auto-differentiation library specifically for awkward arrays, since there are a lot of auto-differentiation libraries available, and it would be rather wise to reuse them rather than coming up with another auto-diff library just for awkward arrays. So even before we start discussing differentiation, it's pretty important to know how JAX and awkward arrays interoperate. So JAX exposes a JAX class type called device arrays, which is used as the primary data type for differentiation. We are currently using DLPack to achieve zero-copy interoperability with JAX device arrays. And what is DLPack? DLPack is just a C header specification in which we can wrap a data buffers and import from or export to many ecosystems like CoPy, JAX, and many ecosystems actually use DLPack like CoPy, JAX, and TensorFlow. So even if JAX wasn't involved, it was really good to move away from CODA interface in support for DLPack, since you can do CPU and GPU export and import too. So the following pictures show how you could do that. So if you do an awk.from JAX on a JAX array, you'll get the awkward array. As a syntactic shortcut, awkward array itself accepts JAX array in its constructor, so you can do that. Also, awk.toJAX can make awkward array into a JAX array. The only constraint is that to go from awkward array to JAX, the data has to be linear, directly linear. It can't be ragged. Okay, so now jumping into differentiation, we can start with an easy case of using NumPy ufuncs. So what are ufuncs? NumPy universal functions or ufuncs are functions that allow operations on any class that implements the NumPy array ufunc class. And these functions include functions like numpy.square, square root, sine, cos, tan, and also bitwise operators. So in this example, what we have done is that we accept an array. We do such a slice that we ignore the last element of the array and we square it up. So my choice of a primal here is a list offset array. And it's like 1, 2, 3, an empty list, and then 4, 5, another sublist. So after this slice, you'll just get like 2 sublists, 1, 2, 3, and an empty sublist. And my tangent would be to differentiate with the second element with respect to the second element of the first sublist. So it would be 2. That's why I activated the input there. So I'm using Jacobian vector product as my choice of auto-diff tool within JAX. So what JAX.jvp takes is the functor, the function, a tuple of primals, which is my list offset array, and a tuple of tangents, which is list offset array underscore tangent. It spits out 2 values, JVP value and JVP grad. So JVP value is the result that the function would give when you just pass a primal. It's just a normal execution. So as you can see, it gives the correct answer. So 149 and an empty list. And JVP grad, so the derivative of x squared becomes 2x. So 2 into 2 is 4, and you get the correct answer. So, okay, so before moving on to the more complicated examples like slices, I'd really like to get into like a prelude to JAX technicalities. So it kind of shows why we had to do stuff the way we did in the following slides. And of course, so JAX does a number of fantastic things behind the scenes. So if you'd like to read more about it, you can check out the autodidacts documentation of JAX. However, this is just the things we used, the internal detailing we used of JAX to solve our problems. So JAX uses something called pi trees as a way to expose these JAX transformations like JVP, VJP, or like in a more general term, forward differentiation, reverse differentiation, JIT compilation for other data containers other than device arrays. And to implement all of this, we need to tell JAX how to break this Python data container into linear buffers and how to reassemble them back into this Python data container structure. So that's PyTrees. And the second important point is that these linear buffers then get just very early into the computation, these linear buffers get converted into JAX tracer objects. Now these JAX tracer objects keep a track of all the computations that is happening on the linear buffer. As such, when you try to catch these, you can easily catch these tracers flowing freely through your functions midway through any computation. While this is very good, a very good thing that JAX does, that it enables us to get like a runtime auto-differentiation instead of a source-to-source. But the problem is that it might cause complications since many functions which are not native to JAX might fail completely to treat these tracers as the same way, because these tracers are not the same as the Python data containers. And a very easy example to suggest is the slicing of awkward arrays. Since the slicing of awkward arrays is pretty complex, they can't be mapped onto linear buffers. And that was one of the main problems that we had to solve. So giving an overview of the system, of how JAX interacts with awkward arrays. So in the first step, we have the awkward array. This is a record array, by the way. We flatten this out into a tree structure. So this becomes list offset array, record array, that becomes, and it gets split into, so I guess the more important thing to notice is that this entire complex structure really breaks down into 2 linear buffers or 2 numpy arrays, and JAX only operates on these 2 numpy arrays. When I pass these 2 numpy arrays onto JAX, now JAX uses this numpy array buffers and interacts with awkward array functions to come to a conclusion. And the final call of JAX is using the derivatives that it got from the function trace and use the tree structure to assemble. So we have the linear buffers now of the derivatives and the tree structure. We combine them both together to get a new awkward array. And for convenience sake, this is an awkward array, but this can actually be any awkward array. This record array could be converted to list offset array and union arrays and so on and so forth. So well, let's start with an example. This is how your function would look roughly while doing a differentiation on awkward arrays. So you have your usual imports, and there's one caveat that you need to update your JAX config to and instruct JAX to use only CPU. Since well, awkward array has GPU support, but it's not complete, so you might run into some error that might be hard to debug. So it's always advisable to use the CPU platform. Then you do an awk.jax.register function, which basically tells JAX that there is something called awkward arrays, and when you encounter a function containing awkward arrays, this is what you do. So this function here does a very complex slice. So with regards to the list offset array that I'm going to push into this function, this slice, what it does is it takes the last sublist, so 4, 5. It takes one more instance of that 4, 5, takes the first instance of the list offset array, so 1, 2, 3, and reverses each of that inner sublist. So what you actually have is 5 to 4, 5 to 4, and 3 to 1, and last is 3 to 1. And you raise them all to the power of 3. And then you do a JVP as again you pass the function a tuple of your primals and a tuple of your tangents. So you get the JVP value as 125.64 as we expected. So 5, 4, 5, 4, and 3, 2, 1, which is 27, 8, and 1. And the JVP grad is also correct. So your x cubed get converted. The derivative of x cubed is 3x squared. So 3 into 2 into 2. So 2 squared, or 3 into 4 is 12. So that, but like, how is it working? So this was the view of the array before the slice. And essentially what JAX gets is just this linear buffer, the 1, 2, 3, 4, and 5. But after the slice, this gets converted into a new data buffer, which is 5, 4, 5, 4, 3, 2, 1. Now, the problem is that 1, 2, 3, 4, 5 had a JAX tracer associated with it. But how do we slice this JAX tracer in a way that it represents this data buffer after the slice? So we need to do another get item call. We need to write a specific get item call to handle traces, which will basically map the traces the same way the function maps A to B. So yeah, so that it starts representing the array after the slice. And why we do this is basically because awkward array slices are complex and they really don't map into linear buffers. So this slice, square brackets 2, 2, 0, and colon, -1, this wouldn't even work correctly on this linear buffer. If you just slice this linear buffer, that would give you the wrong result. So we need to do many special things within to make it agreeable so that the JAX traces and awkward array agree on the same format. And how do we do that? We make use of something called identities. So identities are nothing but you can consider them as an identifier to each of the data elements. Or even to think in a more intuitive way, it's the slice you would apply to the original array to reach that data element. So if you do a list of, if you find the identities of this array, you will get this two-dimensional array. And what it does is that if you do a 0, 0 slice on the list offset array, you will reach 1. If you do a 0, 1 slice, you'll reach 2. 0, 2 slice gives you 3. 2, 0 slice gives you 4, and 2, 1 slice gives you 5. And so this is what identity is. Yeah, identities are unique and they basically provide an identifier information to each of the data elements. Well, now the interesting point to note is that these identities get duplicated. So the actual entity of that list or the slice from where it came from, that information is tracked and stored in the next identity. So after the slice, your identities get represented something like this. So, fine. So 2, 1 comes first and it's repeated in the 0th and the second position. So, and 2, 0, which is 4, it's again repeated in the first index and the fourth index. Then 0, 2 which is 3. It comes after that. So 3, 2, 1. The last three elements are 3, 2, 1. So what we do now is that we take the identities after slicing. We take the identities, see the identities before the slice, find the intersection between them, and check where. Okay, so fine. So where basically the 0, 0 lies in the new slice, or where does 2, 1 appear in the new slice, and we do a jax.numpy.take, which basically when you give indices to it, it gives you the correct slice. So it's a way of just putting in indices and getting the appropriate final data slice. So that's what we do. We figure out the correct indices, which in this case would be, let's say, by so 4, 4, 3, 4, 3, and then 2, 1, 0, and pass it on to Jax, and Jax gives me the correct tracer. Sorry, I slice the tracer using that and pass it on to Jax, and that's basically the correct way of approaching this problem. So obviously the argument can be made. So what if there are multiple tracers? So there can arise a case where there are more than one children buffers, and each example is a record array again. So what happens when we have more than one buffer, which results in multiple tracer objects as well? And how do we distinguish between these two buffers? Like, where do I apply this slice which is coming in? So we need to, the main problem here is we need to figure out a way that what tracer is what, and on what tracer should I apply the slice. So this record array again gets translated into this tree structure. It gives me 2 numpy arrays finally as the leaf nodes. And if you notice, these numpy arrays contain this hexadecimal number, which is basically a pointer of this numpy array, pointer to this numpy array. Similarly, this. So the solution is this. We create a hash map which maps the pointers of the numpy array to the index of where the tracer associated to that numpy array is located. So for instance, going back, the hexadecimal number is 0x000 2e4c380. The tracer is on the 0th index of the list, and the other tracer is on the first index of the list. So many slices don't create a copy. They just keep a so many slices don't create a copy. They just shove out a view of the array. So when that happens, you're pretty sure that your pointer remains the same. So you just query this pointer into this hash map of yours, and you get the appropriate tracer. You do the same thing. You find the intersection and basically output the correct tracer, and you're done. But if the slices do create a new copy in case of a complex slice such as this one, where the data pointers don't match any of the data pointers in the hash map, what we do is we use identities to figure out, okay, what element went where, make a new tracer, and then make a new list of tracers, and then pass it on to Jax. Yeah. So what Jax functions do we support? Well, for now we support jax.jvp and jax.jet. They have been tested extensively, and they work for many cases, including scalar, ufuncs, and slices. However, VJP or reverse mode differentiation is an experimental stage. Like, some things work, some things don't. The limitations are posted in more detail as a documentation on the Awkward Array website. Well, the image shows like a JIT compiled code. So if you do an np.sign, or basically a ufunc, do a slice again, and it's a list offset array. The tangent, you don't need the tangent. So if you find the JIT value, you just do a jax.jet func and pass on the function arguments, and yeah, JIT value gives the correct answer. This is, you can also use this as a decorator, so that's not an issue. Okay, so finally the future work that's left. So one of the main problems that we ran into while solving jax.vjp is that there was a disagreement in how awkward arrays treat scalars and how Jax treats scalars. So awkward array scalars are really just Python numbers, while Jax scalars are essentially zero-dimensional arrays. So what happens when you do a jax.vjp is that jax.vjp creates a function trace where it keeps note of every data type that it gets and at what step what data type it needs. So when you pass something like so suppose your function outputs a final scalar and jax.pjp needs a scalar to find the gradient. When you do that, what happens is that scalar is something that Jax doesn't know what are Python scalars. So it just doesn't flow through the entire function and just returns an error. So what you can do to come across it, to navigate your way across it is do a slice, which is essentially 0:1 instead of array of 0. So this essentially becomes a one-dimensional scalar, and since that's an awkward array again, it would work, and jax.pjp works on that. Second, like there are some specialized functions like some product that must be implemented in terms of Jax primitive, so that function containing these smaller functions can be correctly differentiable. Again, like since jax.pjp and jvp are building blocks of differentiation, they could write higher utility functions like jax.jacobian.grad and jack forward, which basically automates the tangent finding process. But we can pretty much do that easily since we have the building blocks of auto-differentiation. And finally, we'd like to have more awk.star functions like awk.sum, awk.product, awk.capital array, so on, to be defined in terms of Jax primitives, which would allow for a lot more operations in the functions, like without having to worry about some trivial operation driving all the gradients to 0. And a very good example of this is, suppose you have a slice and your function slices an awkward array, but then for some reason you wrap that slice into an awkward array again. What happens is that drives the entire gradients to 0, because we know that awkward array is an identity function. However, Jax doesn't know that. So it just, as a side effect, it just drives everything to 0. But if you just take the slice, it will be fine. Yeah, that's one thing we need to do. And yeah, thank you. That was my IRIS-HEP project. Thank you for your attention.
Well, thank you, Anish. Are there questions? Thanks again, Anish. I think it's really interesting. I guess this all essentially lands in an awkward release that's either already done or coming soon.
I think it's coming soon. I mean, it's already in the main branch, so I think the next release will have it.
Okay, thank you again. So thanks everyone for coming today, and we'll talk to you soon.
Thank you.
Okay, thanks. Bye-bye.
Thanks.